Okay, let's get started. So last week we were talking about calling conventions, and so calling convention defines what the callers do, what the callees do, and for different compilers, different developers, as long as they follow the same convention, so their program can talk to each other. And in this class, most of the functions you are going to say will be compiled using this calling convention. It's called say declare. Not necessarily all the functions will be compiled this way, but most of the function will be compiled this way. Okay. So getting familiar with this calling convention will help you know how to hack. But there will be some challenges that they do not follow this convention. So for every challenge, as long as you see the disassembly, you understand every line of instruction, then you should be able to hack them. But most of them follow this. So in this convention, the caller will do this, right? The caller will push arguments onto the stack. I'm talking about 32-bit, from right to left, then execute the call instruction. The call instruction will push the address of the next instruction onto the stack, then move the destination to the EIP register. The callee will push previous frame pointer onto the stack, which is the EBP, and then set up a new frame pointer, which is move ESP to EBP. We will have some animations for this later. After that, it will create some space for local variables. Usually it's just a subtract some numbers from the ESP. Then when it returns, when it finishes its business logic, it makes sure that the stack is consistent, and also put the return value in the EAX register. So we talked about there are some prolog instructions that are usually used. Push EBP, move ESP to EBP, subtract something. Correspondingly, at the epilogue of the function, we usually have move EBP to ESP, pop EBP, then return. Okay. So next, we are going to look at some concrete examples. So this is an example you already say before. You already saw this one. So this one has a global and a local variable, and this is a function, a simple function. It has two local variables. Then this is the main function. The main function is actually very short. It will subtract something from the ESP, right? It's reserving some space for local variables. Push a value, A here. What is A? What is A in hex? It's actually 10, right? So the reason we have a 10 here is that because the main function calls func 10 there, calls func 10. So that's why there is a push 10. Okay, that's passing a parameter. So after that, it will make the function call to the func. Okay, so before make the function call, it will push the parameter. In this case, there is only one parameter here. So we will skip this part because we have a more interesting example to show you. Before we show the example, so this is a figure that you should get yourself familiar with. So this is what the stack looks like in most of the functions, as long as they follow the say declare convention. So when you are executing that function, that EBP register will point to the saved EBP, which is a previous function, the caller's EBP. That value will be pushed onto the stack, and the EBP points to that. Then 4 bytes higher than that will have the return address. So this is for 32-bit. Then higher than that, we will have different arguments, because the arguments will push from right to left. So the first argument in the function prototype will be the last one to get onto the stack, right? So the argument 1 will actually have a lower address than argument 2. So this is above what EBP points to. Then lower than what EBP points to will be local variables, will be the stack frame for the functions this function calls. Okay. So let's do a little quiz here. We have an instruction, move EBP minus 8 bracket to EAX. So what does this instruction do? What does it look like? So what does EBP points to? EBP points to the saved EBP. The EBP minus 8 will be what? Will be lower, right? Will be local variables, right? Then another one, load effective address, EBP minus 24. This one is actually decimal. And move EBP minus 24 to EAX. So we are actually loading an address. The value is EBP minus 24. So then what is this address? Most likely still a local variable. It could also be the frame of the function this function is calling. What if we have some positive indexing here? EBP plus 8. What would that be? Which one? Yeah, that's actually the first argument. So EBP points to the old EBP. EBP plus 4 is a return address. EBP plus 8, it will be the first argument. So the EBP plus 12, this is 12 in decimal. So this will be the second argument. So now we understand that, we're going to look at several concrete examples. So this is a factorial algorithm to compute the factorial of an integer. Obviously, if you took the algorithm design class, there is a dynamic programming way to program this, which is much faster. So this is a recursive way to program this. We have a main function. The main function takes 2 arguments. The first argument is the program name itself. The system, the OS will give it, so you don't need to type anything. Second argument, you need to type an integer. Of course, this program has a lot of bugs. We don't have a check to check if your input is can be converted to that, right? So that's not the purpose anyway. So here, we're going to convert the command line arguments to an integer, then put that integer into to compute the factorial of that integer. Okay, so how do we do that? We just recursively call this function itself. So fact n, we will call fact n minus 1 times n. Okay, so this is not a smart implementation of this. Using dynamic programming, it will be much faster. But I want to use this one to show you how the stack works. So this function, this is a say function. This say function calls itself. Okay. There is only one copy of the code. In the memory, in the source code, only one copy. But every instant of this program, this piece of code when it's running, it has its own stack, okay, stack frame. So this piece of code may execute n times, and each time it will have a stack frame, even though there is only one copy of source code. So in this program, we will first print out the address of this parameter, which is also on stack, right? This is the first argument, basically. Then we will print out the value of n and also the address of n there. Then when we execute this program, what do you expect to say here? We are going to say the address of this n, right? So that address will get higher or get lower? It will be lower, actually. So if we execute this program on our server, fact let's do move 5, okay? So we execute this program. we compute the factorial of 5. Okay. So we're going to call this function 5 times. Okay, this piece of code will be executed for 5 times. So fact5 is the first function. Fact5 calls fact4, then calls fact3, calls fact2, calls fact1. Fact1 returns to fact2, which returns to fact3, fact4, fact5, right? Here we're not showing the full picture of that. It's going back, the return. We're only showing that it's calling. But you can see the address. The first n, first of all, each parameter, even though at the C code, there is only one n, but at runtime, there are many different addresses. It's kind of like local variable, okay? So the address gets lower because the function frame of the stack frame of the fact5 is like here, the fact4 goes here, 3, 4, right? It's always go down like this. You can see the address 50, 30, 10, F0, D0. So in this case, actually the stack frame for each instance of that function call is like 32 bytes. You can clearly say that it's 32 bytes here. So the next example will show you how to pass the parameters. Another simple function which take 5 parameters, A, B, C, D, E, right? Like we said that according to the convention, we're supposed to push E first, then D, then C, B, A, right? But let's say the disassembly of this code to verify whether that is true. We go to 5 parameters. So the tool we use is just obj dump -d to disassemble -m for the syntax. I do entail syntax here. If we do not do this entail syntax, it will show the AT&T syntax. It's a little bit different from what I show in my slides. Yeah. So we do the entail syntax, then we go to the main function. So the source code here, let's say the source code here is we're calling this function using parameter 1, 2, 3, 4, 5. Okay. And who is making this function call? To the func. The main function is making that, right? So it's the caller's job to push the parameters onto the stack, to pass the parameters. And this is the piece of code that does that exactly, right? So here we can say there is a function call. It's a call instruction to func. This is a relative address of that. Doesn't really matter in this case. Okay. You see that we're calling that function. Before we call that function, there are 5 pushes. Okay, we first push the rightmost one, which is 5, then 4, 3, 2, 1. Right. So after that, the caller will actually balance the stack here a little bit, but we can skip that for now. So there are other conventions as well. For example, in C code, most compilers also support a fast call convention for 32-bit. What you need to do is you define a function and you add this attribute fast call there. Okay. So how do you make this faster? Can you guess how do you make this faster? So now we pass parameters, we push parameters onto the stack. So basically, we're moving something from the register to the memory. How do we make it faster? We just use registers to do that, right? The register is part of the CPU. memory is outside the CPU. It can be 100 or 1,000 times slower than directly accessing a CPU. So in 32-bit x86, the fast call convention will ask the compiler to pass the first argument using the register ECX, and the second argument using the register EDX. Okay. So basically using two general registers to do this. So if you have 5 parameters, the first 2 will be passing using registers, a little bit faster. We do not have enough registers to pass all. Okay, in 64-bit, the first 6 registers, the first 6 parameters we will use register to do that. So we actually, yeah, go ahead.
What happens if you call fast call with only one argument?
Then the first one will use ECX. The EDX will not be used.
Okay.
Yeah. So yeah. So I think I have an example here. So this is the fun. Yeah. Oh, this one, which code is it? Oh, it's a global variable. Okay. This one is not the 5 parameters. So it's a global variable one, which is this, the source code is here. So, yeah.
So 32-bit by default, no argument.
No, what? No arguments, then we're not pushing, we don't need to push any parameters onto the stack because there's no argument.
So 32-bit, we don't use registers for storage argument.
Default? No. Yeah.
With fast call, we can.
Yes. Yeah. So this is a source code here, right? This is a func. It has only one parameter. This is exactly what you asked there. Only one parameter. And you see the source code here. The parameter is not on stack. Instead, it's let's see. Here. We're calling func. Okay. There is only one parameter. If it's a say declare, we should push that. In this case, we're not pushing that. We're just moving turn to register ECX. Then we go to the function call. Question?
Yeah, are there downsides to this? Is there a reason that it needs to be a special parameter that's added and not default?
The problem here is when you are using this register here, which means if this program, the caller, is using this register, then you still have to reserve this register, right? Then if this program, let's say this part is using ECX, now you have to use ECX for function call, pass parameters. Then you need to still reserve that. You need to push that onto stack, then later restore that. So it's not necessarily faster for all the programs.
Yes.
The fundamental issue here is because we don't have enough registers. Yeah. Yes. 64-bit things are much easier because we have many more general registers available. So in 64-bit, the first 6 arguments, they are already passed by default. They are passed by registers. We will have examples to show that later. Yeah. We don't need to push them onto the stack. And that actually will make our attack much harder later. Because in this class, a lot of the attack we're doing is memory corruption attacks, right? We're trying to overwrite memory. But if the piece of code is not using memory, it's using registers, there's no easy way for us to directly override that, but we do have techniques. It will be the second half of the class. Okay, for 64-bit x86, then the first 6 arguments will be passed using registers instead of stack. And those registers are RDI, RSI, DX, CX, 8, and 9. So if you have more arguments, they will still be pushed onto the stack, or the first 6. So most of the functions, it can cover a lot of functions, right? So the reason we can do that is because we have many more registers available. We have been revisiting this figure a lot, and you can clearly see that the difference between 32-bit and 64-bit. Longer registers and more registers. So the same piece of code, 32-bit, we saw the push 5, 4, 3, 2, 1, right? Now if we go to the 64 bits, this is a 64-bit version of the same C code. This is the main function. The main function makes a function called func, and before that, it passes parameters. And the parameters are, the first one is EDI. In this case, actually, it's using EDI instead of RDI because the value I put there is an integer, not a 64-bit. Then 1, 2, 3, 4. They are just moving into registers, yeah, instead of pushing to the stack. So this piece of code is also faster than the previous one because you're not talking to the memory. Okay, so a similar quiz than before. This is 64-bit. If we're accessing RBP -8, the memory location, and move the value to RAX, what are we moving? It's similar to 32-bit. 32-bit is EBP. Now we have RBP, but RBP still points to the saved RBP. So it will be something lower, right? So this is very likely still be local variable. The second one is also getting a local variable address to RAX. Then if we are accessing function arguments, previously we're accessing EBP +8 +12. Now we're actually doing RDI, move RDI to RAX, RSI, those kinds of stuff. Then if we want to set up parameters, we're not pushing anymore. We're doing a value to move to RDI or RSI. Okay, finally, I think we get the background knowledge out of the way. Okay, finally, we're doing some hacking. Okay, so this will be our very first hacking. We are going to overwrite some local variables. So it should be Overflow local 1 on our platform. The challenge is called Overflow local 1. Forgot to put 1 there. Yeah.
What is an RBP +8?
RBP +8. Okay. So RBP points to the saved RBP, which is 8 bytes in this case, not 4 bytes. So RBP +8 will be the return address, which is also 8 bytes. Yeah. So RBP +16 is hard to tell. If the function has more than 6 parameters, it could be a parameter. If the function doesn't have more than 6 parameters, it could just be the address for the caller. Yeah. The seventh argument. Yeah. The seventh argument where RBB, yeah. The first six will be on in registers. Yes. Yeah, because EBP is 32 bits. RBB is 64 bits. Okay, let's look at our very first hacking. So this is one you are really hacking it, try to get a flag here. So, and this is the easiest one. It will get harder and harder over the semester. When I say easy, first of all, this program has a function called print flag. Okay, you don't need to implement this. It works. You just need to call that, make the program to call that. So the main function takes two arguments, command line arguments. Whatever you input, it will directly give that to the vulnerable function. So that's why I call it vol-foo. The vol-foo takes two arguments. The first one is an integer. The second one is an address. The integer doesn't really do much. The integer will first assign a value to a local variable j. After that, we have a local variable, which is a buffer. At a C code level, this is a C code level, it's 6 bytes, okay? The compiler may give more bytes than that, okay? You don't know. At the assembly level, disassembly level, it may be bigger than 6 bytes, but at least at C code level, we're asking for 6 bytes. Now, after that, we have a string copy. We'll copy in whatever you put in your command line arguments to this buffer. String copy will only stop at the end of your input. So your input could be longer than 6 bytes. It's possible, right? Then we check the value of j here. If the value of j is not 0, we will print flag. Otherwise, the program will print IPT the full, then return. Okay, that's it. So the input here to that j is hard-coded. It's always 0. Okay. So no matter how many times you run this program, you do not buffer overflow here, j's value will always be 0, so you should always print IPT the full. Okay. Then this is the binary code of the vulnerable function, which we will analyze line by line. For that, let's take a look at how string copy works. So I believe everyone who ever programming in C used the string copy at some point. This is a vulnerable function. This is a dangerous implementation. So now, if you in your C code you call string copy, the compiler will give you at least a warning, right? The compiler will say you should not use this function because it's not safe. The reason it's not safe is there are many reasons. There are many reasons this function is not safe, but what we care here is the length. You do not tell this function how many bytes, how many characters you want to copy, right? This program will copy the full source string, which can be huge, but it doesn't care about how much bytes you have at the destination. That's why you could overwrite. So one implementation of this is like this, right? You just do a for loop. You check if the source is end of a string, which is 0, right? If it's not 0, then it will keep copying from the source to the destination. At the end, you will add a destination and a 0 there, and just to return the pointer there. Okay. Of course, shorter implementation can be like this, only 3 lines of C code, but it's equivalent. Maybe if you write this code, you write this code, the generated binary code will be a little bit shorter, but the functionality is the same. So now you understand how string copy works, and you understand the string copy may overwrite the destination, and destination may not be long enough to store whatever was originally at the source. Okay. Next, let's look at, we are going to look at this piece of code line by line, try to understand what problems this will cause. So right now, assuming that the main function just called the Overflow, So the next instruction to execute is the very first instruction of push EBP, the very first instruction of Overflow. Okay. So we are here, we're going to execute this one. So the instruction we just execute, which one was that? Just a call Overflow, okay? That's the instruction. And that instruction is in the function main. Okay. So what does that instruction do? The call one. That instruction will move, will push. No, push argument is before that instruction. Yeah. You're right. We're pushing the arguments before that call instruction. So that call instruction, what it does is to push the address of the instruction after the call instruction onto the stack, right? Yes, then we change the EIP to here. Okay. So now what the stack looks like? Stack should look like this. Okay. We have two arguments here. One is 0, another one is the address, remember, right? So those are already pushed onto the stack. So we have a I, which is 0. We have P, which is the address. So already on the stack. Then we have the return address on the stack. And the ESP points to here. Okay. Because call implies a push there, right? So that's why the register ESP points to here. Now we're going to execute. Yeah, go ahead.
We could have the address of the next instruction, right? On next
No. EIP has the, what do you mean? ESP, so SP is a stack pointer, always point to a stack. Yeah, you should. Yes.
The call will actually push on top of the stack the next instruction.
Yes. Yes.
The ESP should be pointing to the next instruction.
The address of next instruction. Yes.
But it says return.
No, the return here doesn't mean a return instruction or whatever. It's just a name I gave to that address. I call it a return address. Yeah. It could be any instruction. Yeah.
Whenever we push argument into a stack, it goes from high to low. Or...
Yes, from high to low. Yeah.
Okay.
Yeah.
And where is the EBP?
EBP right now is somewhere up there. So technically, right now we are still executing in the main function. So the EBP at this point actually points to the saved EBP in the main function's stack frame. And that saved EBP is whoever called the main function. Usually it's a libc start main whatever function. Yeah.
For the underscore start function,
that will the underscore start will be the very first function. There will be many functions in the between. Eventually you call the main function. Yeah. The function actually called the main function is maybe underscore libc start main or whatever. Yeah.
Yeah, but for like when the whoever calls underscore start,
yeah. Not necessarily. I don't record. Okay. Yeah, you need to debug to figure out what's going on there. But it will be the interpreter's library's job to set up those registers to make sure whatever is correct. Yeah. Okay, now the first instruction we are going to execute is push EBP, right? So what I'm showing on the right-hand side is the after effect. So after the first instruction, what do we have here? We are going to push whatever in the register EBP to the stack. Means Now we have some 4 bytes here, the old EBP, and ESP moves down from here to here, right? Then after that, we are moving ESP to EBP. EBP is a register, ESP is a register. So in this step, we are not changing the memory. We're not changing the stack. The EBP previously points to somewhere much higher. Now its value is copied from ESP. The reason we are pushing the first instruction we push it is we want to save its value. We're going to use it, right? Now both EBP and ESP now points to the saved EBP. Okay. That's what we have been talking about at the beginning of the class. EBP eventually points to the old EBP or saved EBP. Now, after that, we have the subtract 18 in hex from ESP. So EBP doesn't change. Okay. During this function, the EBP doesn't change. Of course, this function will call other functions, and in those functions it will change. Then ESP will move down to, this is like, how many is this? This is like 24 bytes, right? 18 in hex is actually 24 bytes. EBP moves here, ESP moves here, points to here. So this is the prologue I've been talking about, those 3 instructions. Right? Push EBP, move ESP to ESP, subtract something. Now we are going to move EBP plus 8. Whatever EBP plus 8, we're getting 4 bytes of that address. Move the value to register EAX. So what is EBP plus 8? EBP is here. EBP is old EBP. Save EBP plus 4 is return address. EBP plus 8 is the first argument, right? In this case, the first argument is an integer. We're moving that integer into 0 into a register EAX. Okay. Then we're moving that value again to EBP minus C. Okay. Previously, the EBP plus 8, which is a parameter. The EBP minus C is EBP lower, so which is a local variable. I'll talk about that many times. So we're moving that 0 to a local variable, and that local variable is actually our local variable J. So now we know that our local variable is actually at EBP minus C. That's its location. So this is a relative location, right? This local variable only has a relative location. Its location is always 12 bytes lower than where EBP points to. So there are many different instances. There can be different instances of the same function, but they all have their own copy of the local variable.
So that 0x 18 would based on the number of the size of the local wave.
Which one?
Or is it standard?
Which one?
Because we push change the instruction.
The subtract?
Yeah. So that 18 is the based
Yes.
on number of local waves. Will be more.
Yes. So obviously, at the C code level, you don't see that, right? The compiler will decide what to do there. The compiler will compute how many local variables we have. The compiler will also think about other things like alignment. So the compiler can put some paddings there because for hardware reasons, if those bytes, those variables are aligned, they may be accessed faster. The compiler has those kind of information as well.
And initialization inside the function that is analyzed function then updated.
Initialize local variables, or
So it's the local variables that declared somewhere in between the function. So it's
okay?
the compiler doing one part, figuring out.
Yes, yes, yeah. So after that, we say the compiler will subtract from ESP again. So the ESP will move even lower. So now the ESP actually points to EBP minus 20. Okay. Previously it was minus C, now minus 8 again. the minus 20. This is where ESP points to. Now we are going to do a push. We're pushing what? EBP plus C. So EBP plus, which means a parameter, right? EBP plus C is the second argument. Plus 8 is the first argument. Plus C is the second argument. So we're actually, did I move that? Where are we? Over here, yeah. So we're actually pushing EBP plus C, which is this value, onto here again. Okay. So we're copying this value from the parameter to here again. The reason we are doing that is, let's see if we go back to the source code. The reason we are doing that is the string copy core is using P as a parameter, all right? The second parameter. And we are setting up the parameters for string copy. How do we set it up? We push. We push P. Yeah. And the P is from here. That's why we're doing our push.
What about jar box?
What? Yeah. Yeah. So because it's not initialized, right? The only thing you need to do is to reserve some space. And that subtract already reserved some space for it. But right now we don't know where it is, to be honest, right? So how do we know where it is? It's going to push this value onto the stack. It's going to push the address of the buffer onto the stack. And the address will be somewhere a little bit higher. Yeah.
That's why we did the subtract minus 8 by.
We're not there yet. It's actually, no, it's, maybe, yeah, maybe, yeah. So let's say we have a push here, right? This is the push to P, the second parameter. Then we know what we're going to push next. This address, here we're going to push the address. And this should be the address of the buffer. The buffer will be somewhere here or somewhere here. We don't know yet, right? So basically this is a pointer. Pointer will point to here or here. So how do we get the address of that? Two instructions to do that. The first one is EBP load effective address, EBP minus 12 to EAX. Then we push EAX, which means the address is actually EBP minus 12 in hex, which is EBP EBP 12 is 18. Yeah. So then now you can say this will be the stack. The buffer will be at EBP minus 12. The local variable will be at EBP minus C. Then what is the size of that buffer? It will be 12. 12 is 18, right? C is 12 in decimal. So this is exactly 6 bytes. Okay, at C code level, we asked for 6 bytes, and the compiler is giving us exactly 6 bytes of this. So after this function, the Overflow function makes a function call to string copy. It's not showing the name here, but this is string copy. But you know that string copy is a dangerous function. The string copy will copy whatever your input is to this place. But this place is only 6 bytes, right? Then the problem here is if you input 6 bytes, what will happen? It's good. It will copy that 6 bytes, and actually the string copy will add another 0 at the end, right? But this value is already 0, so it doesn't matter. Okay. But what if you copy 7 bytes? You will overwrite the local variable j, right? So the j will not be 0 anymore. J will have other value. What if you copy much more? Let's say from here to here will be 18 bytes, right? What if you overwrite 18 bytes or 19 bytes, then you are going to overwrite the old EBP, right? If you overwrite more, you're going to overwrite the return. You can overwrite everything which has a higher address than this, right? So let's say if we need to look at the rest of the instruction here. Yeah, I think we can look at the rest of the instructions a little bit because it will help you understand. Maybe let's do the demo first. Let's go to overflow local 1. So 3 of you already got the flags there. So if we run this program, it will not do anything. I thought it would print IPD the full. Oh, if we do not have any argument, it will not do anything, right? If we have let's say, I put 5 characters there, it says IPD the full, right? If I put 6 there, it also says PD the full. If I put 7 there, doesn't really matter what I put, okay? As long as it's not 0, it will call this print flag function and give you the flag, right? That's it. So this one is very simple. But what if we do much more than this? Like this. I don't know if this is not actually. Oh, it actually is. You see the difference between these two? What's the difference between these two?
Presence of the segmentation fault.
Yes. So why do you think there is a segmentation fault?
We have gone so far that we have terrible remembering the names of the registers, but we are not returning to the correct place anymore.
Yes, that's correct. So basically what happens here is how many bytes we put here? 1, 2, 3, 4. This is 6. This is 12. This 18. So I put 28 bytes there actually, right? So when we write 28 bytes, if we see this figure, we're writing at this location. From this location to this location is 18 bytes. Okay. But I put 22 bytes there, which means we overwrite the saved EBP here, the old EBP. So when the function leave, the leave is equivalent to move EBP to ESP, then pop EBP, right? So then we're going to pop whatever is here, which we overwrite to the EBP. This is supposed to point to the previous function's stack frame, which has a return address. Now we are giving a garbage address here. So that pop eventually will lead to a memory access at that location. And that memory access could be illegal because that address may not exist, may not mapped, right? That's the first opportunity to have that segment fault. Even if that address is a legal address, it's accessible, it doesn't have the stack frame we want. It may be just some garbage value there. And on that stack frame, there's a return address and also saved EBP. And that return address, when the CPU tries to execute from there, may trigger another segment fault, right? But what we're trying to do in this class is we do not want to segment fault. We want to exploit those things. So we put 22 bytes there, and they got this. But if we only put 18 bytes, if we put 17 bytes, technically we should not get that, right? So I think this is, looks like, yeah, this looks like 17 bytes. And remove the 17 bytes, we should not get a segment fault, okay? We only get a flag, no segment fault. One more byte, I think. One more byte, because one more byte, we're going to overwrite 1 byte of the save the EBP to 0, unless that is already 0. Otherwise, this should give us a segment fault. Yeah, so this one give us a segment fault. So originally probably it was not 0. Make sense?
So as I'm trying to wrap my head around what we're doing in this class, could I change that EVP to something else I want to run?
Exactly, we can do that. So what we are trying to do Thursday is we're going to change the return address first instead of EBP, because the EBP is a little bit harder. So after that, next week we are trying to go back to that figure. Go back to the figure. Here we are having a sequential override, right? So which means before you override the return address, you actually can override the old EBP. Okay. But the return address is the address that you are going to execute code directly. The saved EBP has another return address at the upper layer of the function call it will return to. So if you can directly override this one, then this one doesn't really matter. Okay. Eventually you will get segment fault, but before that you already get what you want. Okay. That's why we're going to override this part first, then we override this part. Then after you override, the question is where you override it to. Then you can inject the code. So at the beginning, next week, what we're going to do is we're going to inject some shellcode in the address space. Okay. That is the original buffer overflow idea. However, in the last 15, 20 years, CPU come up with new features. OS has been changing a lot to defeat those kind of attacks. You will not be able to inject in the later half of the class. You will not be able to inject the share code directly there. So we're going to directly use the code pieces, the code gadgets in those address space, chain them together to do arbitrary computation. And that is called return-oriented programming, the second half of the class. So go back here. If we already tried that, right? So if we do like 18 bytes, we're going to get a segment fault. So when does our class end? 125. Yeah, we still have a lot. Good.
We do like much more than 18 bytes, and I'm not getting it.
So when we are doing more than 18 bytes, we basically override these parts, right? And at the end of this function, there is a leave. So who called this function? The main function called this function. The main function has its own stack frame, which has a return address. Right? Let me draw it this way. So this is Overflow's stack frame. Look like this. It has a saved or old EBP. It has a return address, right? And this one is actually called by the main function. The main function up here has the same structure, okay? It has saved EBP. It has return address, right? Okay, so this is a stat. This part is a stat. Then we also have code part. This is code. This is the main function. This is the main function code. Main function will call, let's say, call Overflow. This is one instruction, and this the next instruction. So this return address, where does it point to? This actually points to here, right? The next instruction of this call, okay? And this main function where points to maybe there is a leap say start main, maybe. I don't remember the name of that function. Maybe this one. Okay. This function has an instruction call main. Then this return address is actually the address of this one. Make sense so far? Okay. Now, and where does this point to? Save the EBP. This actually points to here, okay? So before we're executing Overflow, the EBP points to here. When we're in the main function, EBP points to here. Now we're executing Overflow, the value of EBP is saved onto the stack, okay? So that's why this one actually points to here. So now we are overwriting this address, okay? This is 4 bytes. We're overwriting 4 bytes or 1 byte, whatever. The problem is after we overwrite this, now this one doesn't point to here anymore. It could point to just some garbage value anywhere, okay? It's garbage. When it points to this memory, if this memory is not accessible, when we dereference this address directly, there's a segment fault because this memory is not mapped. Okay? If this is mapped, then the main function, the code will believe what this is will be a, let's say over here, will be a save the EBP and the return. Okay, the main function, the code believes this is what that is, but it's actually garbage here. So when we dereference this one, we get a segment fault. We dereference this one, also get segment fault. Does it make sense now?
But I'm saying if I put like 200 bytes, then I'm not getting segment for that.
You're putting 200 bytes, you're not getting segment fault? Let's try.
And I will get the open the random for you.
Let's print 200 bytes of garbage there. You give me a segment fault.
I will open it the random. Open it.
So it doesn't really matter what you give there, right? So you want to do a open SSL, then what's the command? RAND is this?
Flat.
64?
Yeah, minus
Minus what? Base. Oh, this? 200? Okay, so let's see what you are getting here for this one first. Did you check what you get? Okay. Okay, I think yeah, new line could be a problem. Let's do a what is the hex dump tool we use? XXD. Let's see the value here. I'm thinking it's because, okay, so here we have OA, right? The OA could be tricky. There is no 0. I don't see 0 there. OA is the new line, right? OA is the new line. So this one is not giving us segment faults. Let me see.
We change the plan from this is to go to hex, then I get it.
To hex. Okay. So first of all, it's definitely overwriting that, right? It's the question is why the system is not outputting segment fault. Well, you get a stack, you still get a stack overflow. What do you mean by that?
That also will happen when we put pushing on the stack.
We're not moving things there. We're moving things to the buffer, so we're getting stack overflow. Yeah, we're not pushing things. Yeah. So 200. First of all, look at this. This is not even giving us the flag, right? What?
Just put 7 or 8.
Okay. My feeling is, say this one is not even giving us the flag, right? My feeling is at some point it crashed the program and the program didn't even have a chance to give us a flag. And also we do not see the message of segment fault because this should be definitely overwriting things, right? What we can do is we can actually debug this program, right? So when you say something like this, you cannot explain, you debug it. So we debug this program. Buffer. So we set up breakpoint at Overflow. We run this program. We are running this from command line. So we should just do this. Open SSL. What's the command you're using? Red space 64. Let's do 400. Okay. Hopefully we can. See? The program exits normally. That's interesting. We haven't. It didn't even trigger. Why it didn't trigger that? Okay, let's try 7. See, if we do 7, we trigger Overflow. We do 400. I think I know what's going on. So when we do 400, we didn't even trigger that Overflow. The Overflow was never called. I think it's probably a shell limitation here. The shell doesn't allow us to give a very long input like that. What? The shell. The shell, yeah.
I think it allows because it will keep increasing the zeros.
Yeah.
When I get a message from the terminal that argument is on.
But you can see here, the program just exit. It's not even giving us. It didn't even call Overflow. So what? Okay, it maybe allows, but what's the other case that? Oh, I get it. Okay. What's our program? Okay. Can anyone guess what happens here? I get it. I understand what's going on. What's going on here? The argument, 2 arguments. You have a new line. It's not 2 arguments anymore. That's the reason, right? So we can show that. So now we set a breakpoint at the main function, not the Overflow. Then we do this. Okay. So now we're at the beginning of a main function. So we should be able to print argc here. Okay. So argc. Okay, we cannot say argc. Then we can. Where are we? Let me see. Where are we? We are here. This is part of main function. So how do we get argc? Argc is the first argument, right, of the main function. So it's at EBP plus 4, right? So we just do a print EBP plus Oh, yeah, you're right. EBP plus 8, right? So should I, hold on. Oh, I should exam integer. Oops. Another slash. Oh. So now I means instruction. Should be D. Is that correct? Oh, should be E or H? Let's say we exam. I remember it's H. What?
I think it's also
EAX.
yeah.
No, yeah. Here. Hold on. So ESP should point to the address, right? Oh, it should be X. Sorry. Okay. So size is not correct. Should be GX. GX too big. What is 4 bytes? What's that? Let me Google a little bit. GDB print exam 4 bytes. So B is 1 byte. Oh, W, maybe W, let's say. Okay, no, it's good. So W is 4 bytes. So ESP should point to maybe EBP. EBP should point to the address. Why is EBP? Oh, because it's a main function. The main function's stack frame is a little bit different. But whatever. Do we? Oh, we don't have argc here. Let me say the source code. What is the best way to do it? Well, there's a compare, right? Here, we look for that code, that piece of code compared to oh, here, here. Okay, so we set a breakpoint here. We just step. We're here. We step twice. Step. Hold on. Did I just step? Let's go. How did I get here? I do. Oh, I should do SI instead of S. Let's start from beginning. Okay, now we're going to run this again. We're going to generate 400 base 84. Okay, my theory is what we generate will be multiple command line arguments. So it doesn't. So the argc will not be 2. That's why we never call Overflow. That's my theory. So let's see if that's correct. Oh, we are here. Let's say. So we're going to NI, next instruction, 1 step. Next instruction again. Now we are here, right? So what EAX points to should be the value of arguments. So we exam this at the address of EAX. Okay. The value we get here is 10, is 8. We're not giving 2 arguments. That's because of that. That's why if we do, you guys understand what's going on? Then let's say we do this. We do 7 because it's so short. Most likely there's new line. Okay, and we do this. We should get the value of 2 here. Right? Do 2. Oops. Twice at NI. Now we are at this. Okay, we're at this location. So we exam what EAX points to, and it has 2. Okay, That's a reason. Yeah. It's not because the shell doesn't allow. You're correct there. Yes. But you said you tried like not even longer? Oh, yeah. So the shell so the shell does have a limit, right? If it's too long, it doesn't allow that, but we didn't trigger that. The reason we didn't trigger the bug is because the new line. Cool. Good. I like you guys to find the problems and we figure out here. Okay. So obviously I didn't prepare that. I was like, what's going on there? It should be a problem. I didn't realize there is a arc2 here to compare. Yeah, that's the reason. Cool. Okay. Actually, we have another 30 minutes and I want you guys to hack the second one. And I do not plan to, I will walk around and your job is to get the flag for the second challenge. Okay. So before that, let me show you the homework. So the homework is due before Tuesday's class, which means by every Tuesday, I will release a new homework. And this week's new homework will be like this. So start early, okay? Don't wait till Sunday. You use, the first one is PMAP. The second one is S-trees. Those two are easy. The third one is a little bit challenging. You are going to do reverse engineering, okay? There is a program called RE132 on our server. RE132. You are going to reverse engineer this program and find the secret, okay? After you get the secret, you can get the flag. Okay. You can download this program like this. There's a download. You can download this program. After you download this program, you can use OBJ dump. You can also use other tools. I recommend you to use Battery Ninja, especially for the first project, first homework. Battery Ninja cloud version. It's free. Just register. Then you drag this program there. Try to analyze this. Use this tool, which will be much easier. Okay, so that's the first reverse engineer homework. Then this one is like 13 points. You first explain what's going on there, so I can understand. If you understand, then you can really get the flag. Then you will do buffer overflow 1. Most of you already did in class. Then you will do buffer overflow 2, which you can do right now. And I will walk around to help you. Then you will do buffer overflow 3. There are 2 versions of it, 32-bit and 64. You just choose one. For the previous one, you need to do both versions. Okay. Then there is a bonus point of buffer overflow local 4. Okay, that's a bonus point for 7 points. Cool. Start early. So now let's do this one. Tuesday's class next week. Yeah, you have a week to finish this, but start early. Yeah. Okay, so this one is very similar to the previous one. All right, very similar. Overflow local 1. The only difference is previous one, the value j will compare if it's 0. Now it's a specific value. So previously, as long as it's not 0, you get the flag. Okay, which means it can be billions of values because 4 bytes, that's billions. Okay, as long as it's not 0, other billions of values, okay. Now it has to be specifically be this value. Okay, that's it. So you need to override j specifically to this value. Then you can get the flag. So you need to do a disassembly first to verify the buffer size. In this case, it's very likely to be 6. Then you think about how to override the j's value. Some commands I want to show you. We can use the tool Python 2. We installed Python 2. I assume most of you are using Python 3 right now. But Python 2 syntax is much simpler for what we are using. So you can use this syntax to input something to a program through command line arguments. Okay, so this is the dollar sign, parentheses, Python 2, -c, double quote, print, blah, blah, blah. Okay. I also have other examples if you want to use the pipe, but in this case, you don't. No, this program uses command line. You don't need a pipe. Okay, so we have we have 25 minutes. Yeah, that's the way you reckon. You figure out what that is. J is not. Yes. That's why any value. There. I wouldn't matter when we're I will type it there. Randomly type it. Doesn't really care. No, what they could you need to care. Yes. And I what you need to use. Yeah, I is always there. You overlay. I is always there. Yes. But you can overlay. You can override J.
Overlay J.
Yes, your J is a local variable. And Bob is also a local variable. All right. Yes.
So, so we kind of also override the, the time.
Yes,
Is there-
yes. Yeah. Got a little bit. Cool. This part is this part is the screen. You're giving the screen.
Oh,
Where do you need the head span? This is a head span, right? You're giving the string.
of the diagonal number.
Yes. You can't. You don't have. But that's not. First, we start with how we manage that. Okay, for 2 minutes, let me give you some things. So this is what the stack looks like. It's exactly the same as overflow 1, right? So the buffer's address is EDP minus 12. 12 is 12 being hex is 14. Then the local variable J address is EBP minus C, which is 12, which means this size is the buffer is 6 bytes. Now after that, the J actually only takes 4 bytes, right? 1, 2, 3, 4. So after that, there are still like 8 bytes. This is 8 bytes. So nothing is really here. Okay. Those 8 bytes, nothing is really here. So what we're trying to do is these 4 bytes. These 4 bytes, they have to be the value 1, 2, 3, 4, 5, 6, 7, 8. All right. And this is written in hex, which means each one is 1 byte. Okay? But the problem here is one of the problems is how to include things. Okay. If you're not familiar with Python, that's why on my slides I have the last 2 slides here how to include this. The second one is which byte should go where? Which one is high? This is high, this is low. So for those 4 bytes, this is low address. Right? The low address should have what? The least significant combined or high or most significant combined. This is a little endian. Right? So in little endian, the lowest byte, the lowest address should have the least significant byte. So the least significant byte is what? 78 in this case. So at this address, we need to put 78. This address, we put 56, 34, 1, 2. So if we want to byte by byte, we can do this. Of course, I mean, you can also ask Python to do this. Then how about this 6 byte? How about this? Here. What should we put here? Anything, exactly anything here. Just don't put 0 there. Maybe A or otherwise anything. So then the command we can use is like this. If you want to print hex, just use /x, then hex number. That's it. So let's say so because we're going to print that, we're going to use Python. Let's do a Python first. Use Python Python 2 syntax is much easier, simpler. Do a print. So in this, we're going to print what we want to have, right? So what we want to have, we want to find 87, 56, 34, and 12, right? So if we print this, it will be this, but we can't do all XED to verify that. So the least significant byte should be yeah, I think it's correct, right? So this will be fitting the program first. So this will go to the lower address. So you see, this is exactly what we want. And there's an OA there. So if we feed this program, feed this value, in the program, which is buffer. Here we are not giving that 6 bytes of garbage. So we just put a random 6 bytes and put an A there. Times 6 and 6 bytes, then plus 6, right? So this give us a value. So if you miss 1 byte, you're not going to get it. If you miss the order, obviously, the order has to be this. Okay, so I'm showing you how to get a flag, but you also need to do this for your homework, and also homework. There is another one for 3. Okay. For task 7, I'm not showing you the binary code. I'm not showing you the source code. So you need to figure it out by yourself. There's a bonus points, like I said, overflow 4. Any questions? Of course.
Trying to make sure I understand everything before I. I have not been booked it before they get. Oh. Such a disconnected. I did not see a tag fault. Yeah.
Yes. So this one is not tied into the program, because it's still tied into the program. Is the same like it's taken into client. This program is not taken into client, that's why it's getting it. Now that there's several some there, we saw right and there. That's why I don't want to create this. This one, this is much more straightforward than having two. Yeah, check the home. I think the phone is right on the home. Yeah, but the band is not. The band is. Okay, guys, I think time's up. I know you're not hacking, but someone. Yeah, for a time. Okay, see you guys Thursday. If you have questions, I will be outside.